Okay, so I'm going to take you through the Biotech math quiz and walk you through all the different steps you would take to solve it correctly so that those of you who struggle with this can review it and do a proficiency challenge to improve your score reasonably, but also more importantly, to be able to carry out biotech math appropriately for all of the labs that we are doing this year. So first we're dealing with scientific notation. So here's some quick little steps. Step 1, move the decimal left or right accordingly. Leave only one number between the front of the decimal, okay? Write the number without zeros. Well, there's an exception to that if we deal with sig figs. Except sig figs. Okay, count how many places you have moved the decimal. Make your power of 10, make that your power of 10 moved left, positive, but if moved right, it would be negative. So 3200 would be 3.2 times 10 to the positive third, and 0.0032 would become 3.2 times 10 to the negative third. Okay, so let's apply this. So we are going to move the decimal 1, 2, 3 places. So now it's between the 4 and the 3. So 4.3428. We need to keep that last 0 because that is a significant figure 0. Okay, and then times 10 to the 1, 2, 3. So that tells us that that's 4,342.80. Okay, now there is no decimal place here, so we're just going to start right at here. 1, 2, 3, 4. Okay, so we're going to be at 10 to the 4th, and it's going to be 2.71, but we're going to leave those last two zeros off because those are not significant. Okay, now starting at this decimal, we're going to go -1, -2, -3. So times 10 to the negative third, and it's going to be 7.2. So that is how we solve those scientific notation questions. Now, significant digits. So we have some basic decimal rules. If there is no decimal, then start counting at the first non-zero and stop counting at the last non-zero. If there is a decimal, then start counting at the first non-zero and count until the end. So, no decimal, start counting at the first non-zero and stop counting at the last non-zero. Not a 0, not a 0, not a 0, not a 0. There are 4 of them. Again, start counting at the first non-zero. Okay, 4 of them. So zeros that are embedded between other numbers are significant. These are not significant. They just tell us that that would be times 10 to the negative third if we wrote it in scientific notation. So, significant, significant, significant. Oh, count to the end, significant. So 4 significant digits or significant figures. Now, let's look at multiplying and dividing, adding and subtracting. So when you add or subtract, round the answer to the least number of decimal places. Okay, so in this example we see that this 83.2 could have been 83.172 or 83.214. Excuse me. But we don't know that. All we know is we know it's 83.2. Therefore, the best answer we can have can be to that 10th place. So when we do the math over here, we're not limited at the 10th place. They both have a 10th place. They both have a 100th place. This one has a 1000th place, but this one does not. So we have to stop at the 100th place. So when you do that math, you find that that answer is 2.86. Okay. Again, our numbers, they have a 10th place. This one has a 100ths and a 1000ths. This one does not. We are only certain to the 10th place, so that's as good as it gets. So it's 15.1. Now, multiplication and division is a different animal, okay? You're going to round according to your least significant digits, okay? For example, if you knew you had half of, or you're going to divide 4.4 divided by 2, this is only, that's our least significant digit. It doesn't matter the decimal place. All that matters is that that is 1 sig fig. So our answer will be 1 sig fig, just like up here. This has 2 sig figs, this has 1 sig fig. So our answer can only have 1 sig fig. So when you divide 0.51 by 7, your answer is in 1 sig fig, 4. When you divide 6,880 divided by 21.45, 3 sig figs, 4 sig figs. So therefore, we're going to be limited by our least number of significant figures, which is 3. And so when we do the math and we round, it would be 321. Conversions. Where did these little marks come from? Oh, I know where they came from. Oh, well. So when we do conversions, how many millimeters are in a meter? By definition, there are 1,000. How many microliters are in a liter? There are 1 million. Okay, now unit conversion. We want to take 2,301 milligrams and convert that into grams. So 2,301 milligrams. And then the question is, how many milligrams are there in a gram? There are 1,000 milligrams in a gram. Milligrams cancel out, grams are left behind, divide by 1,000, and our answer is 2.301 grams. Now, 2.990 milliliters, 2 microliters. Now, you could know that there are 1,000 microliters in a milliliter. If you don't know that, you can still figure it out. So let's do it the long way. 2.990 milliliters. So if we're going with real basic definitions, you don't know the shortcut. Well, we know that there are 1,000 milliliters in a liter. Milliliters cancel out. We know in a liter there are 1,000,000 microliters. So liters cancel out. 1,000 cancels out. Cross out 3 zeros. So 2.990 times 1,000 is 2,990 microliters. Next, let's do a dilution. You have 500.0 X DNA stain. That's very, very dark DNA stain. You get it on your hands, it will not go away for a very long time. You want to do a quick stain technique that uses 100 X DNA stain. So we need to dilute it by 1/5. You need 80 milliliters of 100X DNA stain. So, year 1 students, I just asked you to identify what's what. So, C1 is our initial concentration. What's our initial concentration we're dealing with? 500 X DNA stain. What is the final concentration we want? We want 100 X DNA stain. How much of that final volume do we need? We need 80 milliliters. What's volume 1? That's the question. Finally, if you're year 2 or year 3, you had to do the actual work. So we need to use C1 V1 equals C2 V2. Now, we're going to solve for V1. So we divide both sides of the equation by V1. Okay, V1 cancels out on here. Therefore, C1 is equal to C2 V2 divided by V1. Now C1 is, oh, I did that wrong. Do we all see what I did wrong? I canceled out V1. That's our question. We wanted to solve for V1. So let's try again. C1 V1 equals C2 V2. Divide by C1, divide by C1. C1 cancels out, our initial concentration cancels out. So therefore, to solve for how much of the initial DNA stain do we need to use to make 80 milliliters of 100x DNA stain from 500x DNA stain, we would do the following math. Well, 100x DNA stain, that's C1, times V1, which is 80 milliliters, divided by our initial concentration, which is 500x DNA stain. Our units of x cancel out. Our DNA stain cancels out. And when we solve for V1, you find that it's 16.0 milliliters of stock DNA stain. Stock is the original or starting DNA stain. Now, why did I put the 0.0? Well, we had 4 significant figures, 4 significant figures, and 3 significant figures. Oh, wait, actually only 2 of those exist in a reality that matters. This one right here, 500x, 500.0, that actually exists as a solution. 80 milliliters, that actually is based on the limitation of our graduated cylinders. We can go to the tenths place, and with measuring 80, that would give us 3 significant figures. This one right here, we could do better than that potentially, based on depending on our equipment. You could make 100.00x DNA stain, but so that's not going to be irrelevant. Ooh, erase the 100. Okay, so we have 4 significant figures, 3 significant figures, so our 3 significant figures is our limiting factor. So we have 3 significant figures here. 16.0, because we didn't do addition, we didn't do subtraction, we did multiplication and division. So 3 significant figures. There's our final answer.